The design was called Starship V4, and it was engineered to embody the final victory of redundancy over failure. A stainless steel colossus, taller and heavier than any launch vehicle before it, its ambition was simple: to make interplanetary flight a logistical routine. To achieve this, the architecture relied upon an array of 42 Raptor engines, each one an independent power source, promising fault tolerance so complete that the loss of multiple units would no longer signify catastrophe. But in this aggressive pursuit of safety through multiplication, a paradox was immediately written into the code of the system. Every engine added for insurance also multiplied the number of things that could inherently go wrong, stacking the probability against the required perfection. The question engineers quietly faced was not if the system could survive a single failure, but whether a system engineered to eliminate collapse might, by its very complexity, invite it instead. The quiet echo of history was clear, recalling the Soviet N-1 rocket, which failed 30 times, never once succeeding, burdened by a mere 30 clustered engines. Starship V4 was designed to prove that the chaos inherent in clustered propulsion could be managed through software, that rapid algorithms could replace the brute force simplicity of earlier rockets. Physics, however, does not negotiate intent. It only counts the forces that remain when all human attempts at control have finally failed. The sheer scale of Starship V4 demanded an architectural leap that exceeded all previous human construction, standing at 127 meters tall. The Super Heavy booster housed 33 Raptor 3 engines, pushing total liftoff thrust beyond 7,500 metric tons, with the upper stage adding 9 more engines for a combined total thrust of 18.5 million pounds. To support this power, the structure was lengthened, increasing its fuel load by 700 tons to 2,300 tons for the upper stage alone. This immense power network was distributed across the booster's base, coordinated by RaptorNet, a single synchronization algorithm that managed 42 independent controllers. This central nervous system of the rocket governed ignition timing, mixture ratios, and gimbal commands, communicating through redundant fiber loops at a 10-millisecond interval. The architecture was theoretically fault-tolerant, but every meter added to the upper stage changed the vehicle's moment of inertia, subtly shifting the vibrational modes into new frequency bands. While redundancy offered statistical protection, dynamically, the system became vulnerable to sympathetic vibration and pressure surge. The danger resided in the environment of combustion itself, where acoustic pressure at the base could exceed 175 decibels barely a second after ignition. These powerful shock waves interact, reflecting and creating transient standing pressure zones around the outer engine ring. When only 33 engines fired, the pattern of these reflections was predictable, but the addition of 9 more units increased the probability of destructive resonance exponentially. The difference was not arithmetic, but logarithmic, as each new engine introduced dozens of new, complex interference patterns that had never been modeled in smaller clusters. The Raptor 3 engine itself operated with razor-thin margins, chamber pressure at 330 bar, propellant mass flow at 700 kilograms per second, and turbine inlet temperature near 1,000 degrees Celsius. A minute oscillation of just 3% amplitude was enough to induce fatigue in the injector faceplate after a single burn cycle. The immediate solution to this physical hazard was the development of software damping, an active noise control system scaled up to manage millions of pounds of force. RaptorNet was tasked with detecting harmonic buildup and commanding subtle thrust adjustments to disrupt the resonance before it reached a critical amplitude. This strategy relied on the speed of digital computation, but software operates in the millisecond domain, while structural dynamics move in microseconds. The slight difference in these timescales was small enough to be fatal if misjudged. The engine's digital nervous system was significantly faster than the analog wiring that failed the N1, but it was consequently more vulnerable to software-induced feedback, where one recursive correction loop could amplify the disturbance instead of neutralizing it. Furthermore, the continuous scaling had doubled the number of joints, seals, and flanges from the earliest prototypes, making each physical interface a potential leak path or a source of data drift for the controlling sensors. The vulnerability of this centralized control was immediately exposed during the first integrated hot-fire simulation of the new layout at McGregor. After 14 seconds of perfectly aligned telemetry, one virtual engine controller was observed to drift 22 milliseconds behind the others. The system compensated automatically, adjusting mixture ratios in neighboring engines, But this correction propagated too quickly across the cluster. Within 0.3 of a second, 24 engines were issuing micro-thrust corrections simultaneously. The system had entered correlated correction mode, a condition where, instead of canceling out vibrations, the control logic synchronized the errors, amplifying rather than mitigating the disturbance. This simulation, which involved no actual damage, provided the first clear warning, the point at which physics signaled that scale itself had become the primary risk factor, capable of turning perfect control into an engine of destruction. The lesson derived from the correlated correction mode was stark. Every system that is engineered to approach perfection risks exceeding human comprehension. The pursuit of complete redundancy at 42 engines brought the design to a frontier of propulsion that no one had ever stabilized in flight. The design philosophy had inadvertently created conditions for scale-induced fragility, where adding components for safety could generate catastrophic failure mechanisms instead. In the highly pressurized environment of the Raptor chamber, complexity was not a buffer against error, but an amplifier of it, collapsing control margins faster than performance improved. The structural failure of the Russian N-1 rocket was a direct ancestor to this problem, arising because its 30 engines failed due to synchronization issues, demonstrating that a digital nervous system, while faster, carries its own unique vulnerability to feedback loops. The line between total control and total collapse was revealed to be a mere handful of microseconds. The engineering response to this fundamental challenge required a total revision, moving beyond iterative upgrades to a process that engineers internally called an autopsy of success. To break the synchronization lock, the Raptor 4 was designed with a philosophy of control through isolation. The complexity was not eliminated, but localized, and the injector patterns were redesigned for wider tolerance and mixture ratio, simplifying pre-burner sequencing by almost a third. The result was an entirely new combustion paradigm, an organism of autonomous units instead of a delicate orchestra of coordination. The engine's thrust increased to over 320 tons, yet it became more forgiving, achieving efficiency not through dangerously high pressure, but through refined flow paths and improved mixture ratio control. The system now incorporated embedded sensors and predictive modeling within each engine, ensuring that any drift or failure in one unit was managed locally, preventing propagation through the entire cluster. Prior to this systemic redesign, the full consequence of the Raptor 3's fragility was revealed in a late 2024 booster test, ID B10FL3. During the brief 6.5-second burn, engine 21 registered an oscillation in chamber pressure, a deviation of less than 2%. Within 0.9 of a second, the oscillation resonated with two adjacent units, forming a coupled wave that tripled the local vibration amplitude. Analysis confirmed that the structural frequency of the aft thrust dome was dangerously close to matching this resonance, and had the burn continued for just 2 more seconds, structural rupture was probable. The cause was traced to a mere 70 millisecond delay in the temperature asymmetry of a single pre-burner igniter line. This near miss confirmed that the architecture of Raptor 3, while a masterpiece of efficiency, had reached a limit where it demanded more control than the hardware could physically provide, showing that physics had won the argument over human precision. When Starship V4 prototype Vehicle 31 reached final integration, the optimism was high, supported by revolutionary structural and software upgrades. The countdown for the first test flight on June 22, 2027 proceeded without visible fault, leading to a smooth initiation of the ignition sequence. All 33 Raptors ignited, achieving 92% thrust with what appeared for a single moment to be perfect symmetry. But at T+1.2 seconds, the first tiny anomaly appeared when engine 14 registered a chamber pressure lag of 3%. The system's controller issued a correction, which immediately rippled across the booster's thrust pattern. Acoustic sensors captured interference waves reflecting off the launch pad, increasing the local thermal load on 4 engines by 60 degrees Celsius above predicted values. The vehicle cleared the tower flawlessly to the outside observer, but internally, the control system was already oscillating between regulation and disturbance. At 35 seconds into the ascent, telemetry telemetry recorded an unusual growing divergence. Engine Group C lagged Group A by 0.02 of a second, creating a thrust differential of almost 2%. This was mathematically insignificant, but the booster was already under an 8G load, compounding structural stress through the base skirt. The oscillation became more aggressive, with vibration amplitude doubling at 52 seconds. Despite mission control debating an abort, the data remained within range. Then, at 61 seconds, engine 22 spiked to 355 bar, 25 over nominal, and shut down automatically at 62 seconds. Although the booster was designed to survive an individual engine loss, the adjacent units throttled up in compensation, driving the system into a feedback cascade where the very algorithms meant to maintain balance now amplified the divergence. The critical moment revealed how the laws of physics had judged the attempt to achieve perfect synchronization. At 63 seconds, the vibration amplitude peaked violently at 2.4 G. The same algorithms that were supposed to protect the system achieved a synchronization of errors, generating a harmonic wave at precisely the structure's natural frequency. This was the inversion point, where the system's intended safety became its self-destruction. The post-mortem confirmed the logic. The single-engine shutdown created a local thrust gap, and the software's command to compensate produced a counter moment that shifted the vehicle's center of thrust. For 0.8 of a second, the system oscillated in perfect, lethal harmony with its own vibration. The subsequent destruction confirmed that the failure was not a material weakness, but a punishment of precision. Chamber pressures spiked to 370 bar before rupture, with the engine plate's support struts failing in sequence as if collapsing in resonance with invisible music. The collapse of Vehicle 31 taught engineers the enduring lesson that redundancy is not the same as immunity. The control algorithm had been too perfect, too reactive, synchronizing with chaos instead of dampening it. The near-miss analysis was measured in milliseconds. Had the shutdown occurred just 0.3 of a second earlier or later, the phase alignment would have missed the structural resonance. The booster would have survived. But at that precise timing, every factor, frequency, thrust vector, and structure aligned to produce destructive interference. In the aftermath, Starship V4 testing was suspended for 4 months, allowing engineers to isolate and rewrite the synchronization logic. The core engineering correction was the introduction of stochastic damping, a deliberate randomization layer designed to break the harmonic feedback loop. Imperfection became the solution, achieved by introducing micro delays of plus or minus 5 milliseconds between engines to prevent them from locking into resonance. The philosophy of stability shifted fundamentally from absolute control to controlled containment. Furthermore, the engine plate was reinforced with composite dampers and variable stiffness mounts to address the mechanical resonance that the software had amplified. RaptorNet's firmware was rewritten to treat engine shutdowns not as isolated faults, but as dynamic phase shifts, redistributing thrust across randomized, asymmetric subsets rather than symmetric groups. This profound change in approach, from demanding synchronous perfection to embracing minor functional disharmony, had consequences far beyond the test stand. NASA, closely observing the results, reassessed its Artemis timelines, knowing that guaranteed synchronous stability was now a critical factor for crewed lunar missions. The 42-engine vision, once inevitable, was now revealed to be dangerously near its mathematical limit, proving that even the strongest engineering concepts must surrender to the logic of scale. The collapse ironically validated the engineering model. The data produced by the explosion was precisely the information required to stabilize the next variant. Physics had issued its definitive verdict, but it had not delivered its final denial. The program moved forward by accepting the limits revealed in the data, and Vehicle 33 rolled out in late 2028, incorporating all the lessons learned: software randomized, structure reinforced, and engines recalibrated. The next launch succeeded, achieving full ascent, stage separation, and booster recovery, becoming the first fully reusable Super Heavy launch in history. Yet, deep within the telemetry from this and 6 subsequent successful flights, analysts discovered new, unresolved patterns. Small, irregular fluctuations appeared near the upper stage burn phase, specifically minor vibration peaks at 9 Hz. This was too low to be structural resonance, but the oscillation was suspiciously rhythmic, and the team came to call it the heartbeat. Its origin remains unknown, possibly possibly propellant slosh, electromagnetic interference, or an entirely new factor. This faint oscillation poses no immediate threat, yet it endures as an unresolved whisper in a system once destroyed by synchronization. It is a persistent reminder that every time one variable is stabilized, new variables appear in the resulting equations. The initial failure was not a weakness, but a consequence of the system working too well. Every sensor, line of code, and safeguard executed perfectly, simultaneously, and fatally. Starship V4 taught its designers that scale multiplies not just thrust, but consequence. The next generation of flight continues this dialogue with motion and pressure, heat and time, each success a testament to the discipline of containment. The system that once failed in 70 seconds continues to chase the balance between control and chaos. It is a machine built from acknowledgement, where every line and channel carries the memory of earlier destruction, proving that the physics that broke it once is now what holds it together. The engineers will rebuild again, as they always must, inventing new algorithms and forging new margins against silence. They learned that mastery of power is not the same as control, and that complexity, no matter how brilliant, always ends where physics begins. The final ambiguity is written into the data of that first collapse. No one knows whether the next failure will emerge from vibration, heat, or an unforeseen flaw in the software. Only that it will eventually come, because that is the universe's recurring answer to ambition. The margin between triumph and collapse is written not in design, but in tolerance, in how well human intent can coexist with the indifference of the laws that govern it. In the pursuit of perfection, every system eventually meets its own resonance. The Starship V4 stands, still waiting for its next trial under the quiet, indifferent eye of the vacuum.